Okay, so if we have a 4-bit counter, normally what we want the counter to do is we have this counter here. And of course, we're going to have a clock in. So every time, if my clock goes high, if I have a clock action from 0 to 1, then the counter will count 1, right? And do you think if there is anything else we can add to the input of the counter? If you read the project, actually for counter we probably have to provide one more input called direction. So the direction decides if we are going to count up or count down. If the direction is 0, then we count down, which means, for example, previously we have a number of 5, and when we have a clock edge, then 5 will become 4, and after that it's going to be 3. 5, 4, 3, 2, 1, right? And if direction is 1, then it means we are counting up. So if previously we have a number of 5, then next clock we are going to increase the number to 6. And the next one is going to be 7, right? Okay, and if we have a 4-bit counter, obviously the output of this counter should be 4-bit variable Q320, okay? And that stands for 4 bits. And we can also add this input of D320. And this decides the initial condition of the counter. For example, if I count, I have to start either from, like in this example here, I start from 5. And also I can write a different number into the counter. For example, I can load number 4, then we start counting from 4, right? So if we want to load this initial value into the counter, we have to add one more input, and that is called load. So if this input is high, then we load a number into the counter. Does this make sense? Like for example, previously we were counting 5, 6, 7, and next time I want to overwrite the result, I want to start counting from 0 again, then I can load 0 into D320. Does this make sense? Okay, so eventually we get this specification. My pen is not working very well, so let's see if I have this here already. Okay, so we have clock in, that's for sure. We have D320, which is the number we want to write into the counter, and we have the load. If load is high, then we load D320 into the counter, and if we have the input of direction, which determines if we are counting up or counting down, right? So those on the left-hand side, those are the inputs of the counter, and right-hand side, that's going to be the output of the counter. Any question? Okay, and in this simulation, let's do this. So we are going to generate a clock like this, and the clock period will be 200 nanosecond. That means from here to here, this is 200 nanosecond. Okay, so clock high will take 100 nanosecond, clock low will take another 100 nanosecond. And we assume that at the beginning we load 3 into the counter. Okay, we load 3 into the counter. If you look at your project, you have to load 4. So after the EDA tutorial, you have to make a slight change to the code so that you realize what is wanted on the project. Okay, and starting at 300 nanosecond, we start a counter to count down. And if we count down, it means we have to fit 0 into direction. Does that make sense? Okay. So at 300 nanoseconds, the number will be changed from 3 to 2. And after 200 nanoseconds, that is another clock period, then the number will be reduced from 2 to 1, right? And next, we assume that at 700 nanoseconds, we change the direction of the counter to let the counter to count up. So at 700 nanoseconds, the number will be changed from 1 to 2. Does this make sense? So at the beginning, we have a number of 3, and we want to count down to 2, and then we count down to 1, and after that, we count up again, 2, 3, 4, like this, okay? So we are going to realize this using Xilinx. Okay, I'll go to Xilinx, File, close my project first. Okay, and now I can set up a new project. So I go to File, New Project, and I'll name this project as Counter. Today is 31st, 2012. Okay, Counter underscore 10/31st, 2012. And remember, on the bottom side, last time when we built up a logic, which one did we use? Schematic, yes. And this time, we are going to use a different way, because if we use schematic to build up this counter, we have to add a lot of components, AND gate, OR gate, inside the design. So this time, let's try a easier way. Let's use HDL. HDL stands for Hardware Description Language. So we use our code to describe what we want inside the function block. Does this make sense? Okay, so basically we are going to do programming this time. So I choose HDL, I click next, and I'll keep the same device XC3S100E, and I don't change anything else here. Click next. And for the source file, I need to add a source, right? So I click new source, and now I choose Verilog module, okay? When I choose Verilog module, I have to define the file name, and this will be my core, so I'll call it my counter. Okay, I call this my counter, and so make sure you choose this Verilog module on the left side, and you can name it, and click name, next. Okay, so now we have to add the inputs and output of the counter. So look at this block diagram. We need 4 inputs: clock, D, load, and direction. So I start from clock. It's gonna be input, and I'm gonna use bus. And the default MSB and LSB, they are both 0. So that means we only have 1 bit for clock. Does this make sense? Okay. And the next, after clock, we are gonna have load, right? Load, and that's also input, and we have 1 bit bus. And next, let's see, we are gonna have D, which is the initial number of the counter, right? And its input is bus, but in this case, we need 4 bits, right? So which one should I change? MSB, and I have to change it to 3, right? Very simple. And I also have direction, and direction is gonna be a bus, only 1 bit. And next is the output, and I name the output as Q, and it's gonna be output. It's gonna be bus, and we're gonna have 4 bits, right? So that is how I set up the input and the output. Click next, finish, and I don't have to add any new source file, so I'll click next. Do I have to add existing source? No. So I click next, finish. And after that, I have my counter file here on the left panel. Double click it, I open up this file, and the nice thing again, Xilinx wrote down some initial program for us that define the input, output, and this block, my counter, right? And on the top side, everything after the two symbol of slash, that means comment. So they are not part of the real code, okay? It's just comment. We can write down related information. For example, in this case, company, it's gonna be Texas Tech University, and engineer, I write down my name, and also create a date, a design name. I can fill in those information, EDA tutorial 2. Module name is my counter, and on the top side we define the time scale. It's 1 nanosecond, right? So that means when we deal with time, the unit is 1 nanosecond, and the resolution is 1 picosecond. Okay, so go to the bottom. We have the input and output already defined, and the next. So next has something to do with our sequential logic. As we started in our last lecture, if we have a counter, we actually are dealing with sequential logic, which means we have to get something like a memory inside the design that stores the current state. Does this make sense? And in the counter example, the current state is the value of the counter. Does this make sense? For example, if we are counting, so at this moment, the current state is 3, and next moment, the current state is 2. We have to store this number, right? So that next time we only need to do 2 minus 1, then we get the new state of 1, right? So that means we have to create some memory-like thing, and in Xilinx we call it register. So in this case, we have to define our register. So I type here reg, and you can see that if this is something Xilinx can recognize, then it will turn to blue, right? Just in case if we have any typo. So I define register, it's gonna be 4 bits from 3 to 0, and I'll call the register as count. This is just a name, okay? And next, I have to tell the software what I want to do inside the counter. So what we want to do is always at the rising edge of the clock. When the clock turns from 0 to 1, we make change to the output. We update our register. Does this make sense? Okay. And when we make change, we have to change based on the input status. Like for example, if load is 1, then we have to load the new number into the register. If load is 0, then we just count, either add 1 or reduce by 1. Does this make sense? Okay. So I'll tell the software always at my positive edge of clock. So this sentence, it means we do things only at the positive edge of the clock, and CLK is one of the input, right? Clock. So always at positive edge of clock, we first have to determine if we have to load the new value into the register. So if load, which means if load is high, and I'll use comment to write down the meaning of this sentence. So this means if load is 1, then we have to load the new number into the register. So what can we do? We have to load the new number of D into register. So we pass the input D into the register count, right? And because this is hardware description language, we have special operators. So this means we pass the input D into the register count. Okay, does this make sense? Okay. But if load is low, then what do we have to do? We have to count. So else if direction is 1. So this means if direction is 1, we have to count up, right? We have to count up. So if direction is 1, then we have to increase the register value by 1, right? Does this make sense? So we pass count plus 1 into count, update the value of count. Okay. Else, so what's gonna happen if we come to here? Else.
Direction is 0.
Yeah, great, thank you. So this means if direction is 0, then we have to count down, right? Okay, so if that happens, we have to do count be assigned as count minus 1. Okay. Alright, so pretty much that's what we have to do. And anything else? Do you have anything else in our mind? What else do we have to do? So now, at every rising edge of the clock, we have made the decision, we have either passed the input into the register, or we update the register, right? And the next thing we haven't done is we haven't passed the register value to the output. Does this make sense? Okay, so let's guess, what shall we write down here? We have to assign Q as count. So this means we connect the register count to the output Q. Okay? All right. So this should be all the code we have to write for the counter itself. And after that, we can double-click synthesize. And synthesize will try to synthesize the real circuit based on the program we wrote. Okay. Oops. Okay, bad luck. Synthesis failed. We have one error. So go back. Okay, and so this is a good example if you have something wrong. So look at here, the error information told us on line 34, direction has not been declared. So let's check direction. Oh, okay. The reason is right here we used lowercase, right, for direction. So the software doesn't recognize this variable. I'll change it, direction. Okay, after that, try to synthesize again. Okay, so this time we are lucky, and it says that synthesis completed successfully. That's great. So that means we have already built up this counter. Okay, and next we have to simulate the counter and create the time sequence of this. Count down first, then count up, right? So do you guys still remember what shall we do if we want to simulate it? Yeah, but do we have to create something? We have to, so last time we added a test bench, right? So what we can do is we can go to project, choose new source, or you put your mouse here, right click, click new source, either way works. And now we have to add this Verilog test fixture, right? So this is my test bench. Our name is as counter underscore TB, which stands for test bench. Click next, next, finish. Okay, so now this is the code for test bench. Basically, it made connection for the input and output of the counter, and now I have to create the time sequence for the signals. Does this make sense? Okay, and do we still remember what is this? Pound 100. That means wait for 100 nanoseconds, right? So look at this code. At the beginning, it defined those registers. Actually, those are connected to the input and output of the counter we built. And this is the physical connection. We don't have to change it. And here is the real-time sequence for our simulation. So initial begin. At the beginning, every input is assigned as 0, right? And after 100 nanoseconds, then that's what we can do. So we have to finish this code. Okay, let's see. Let's check the logic we want to build. So at 100 nanoseconds, we want to load 3 into the counter. If we want to load 3 into the counter, what can we do? Yeah, we have to load a binary number, either binary or decimal. Actually, Xilinx can recognize both. So, but we have to load this 3 into the counter through one of the inputs, right? So which input shall we use? D, right? So we have to pass 3 into D. Does this make sense? And in order to load the number, we also have to set load to be this input, load this input to be 1, right? So let's do this. After 100 nanoseconds, I'll assign 3 to input D, and I'll assign load to be 1. Okay. Anything else we have to do? Remember, at the beginning the clock is 0, and our clock period is 200 nanoseconds. That means at 100 nanoseconds we have to pull the clock to be high. Does this make sense? We have to also generate the clock pattern, right? So at 100 nanoseconds, clock will be high. All right, and that pretty much describe what we have to do here. At the first moment, 100 nanoseconds, we load 3 into the counter, and the next thing is at 300 nanoseconds, which means the second rising edge of the clock, we have to count down, right? So first I'll do wait for another 100 nanoseconds. I'll pull the clock to be to be 0 again, right? Then I wait for 100 nanoseconds more. I set the clock to be high. But in order to count up, I have to first make sure load is 0. Does this make sense? Load is 0, which means I don't want to load anything from I don't want to load anything from D here. I will keep using the internal register, right? So I set load to be 0, and I have to create the clock rising edge. And for the direction, if I want to count up, then what's going to be the direction? The direction should be 1, right? So load should be 0, direction should be 1, and clock is 1. Does this make sense? So suppose here, and this means, so at the beginning, here is the 100 nanosecond, and here when we pull the clock low, that's the 200 nanosecond, right? And here it's 300 nanosecond. We want to count up. Okay, after that, we have to pull the clock to be low again, right? Okay, and that happened at 400 nanosecond, right? Okay, and we wait for 100 nanosecond more, and then we come to the 500 nanosecond. We have to count up again. Does this make sense? Okay, so now in order to count up, I only have to set clock to be 1. Do I have to change load? No, I don't, because now load is 0. It's still doing internal counting, right? Do I have to change the direction? No, because we want to continue to count. Oh, sorry, I made a mistake. At the beginning, we want to count down, right? So here, go back. The direction should be 0, okay? So we count down. But at 500 nanosecond, we still count down, so I don't have to change the direction, right? So we set clock to be 1, and after 100 nanosecond, we have to pull clock to low again. Okay, then we come to 700 nanosecond, and let's see what do we have to do. Okay, at 700 nanosecond, we have to count up, right? Change the direction. So we have to set direction to be 1 and pull clock to high. Does this make sense? Okay, so basically that is what we want to do to meet the simulation requirement in our EDA tutorial. After that, I'll change the source to behavioral simulation mode. Click this, select my test bench, and double click, check syntax, and everything is okay, completed successfully. So I can double click this this link to simulate. Okay, and after that, I got this window, which is a simulation result, and I have to click one button to show the full screen of simulation. So that is this one, right? Zoom to full view. And here we go. This is a simulation result. For Q, we loaded, oh, sorry, Q is the output, right? So at the beginning, we don't know the Q. And after 100 nanosecond, we loaded number into the counter. So output becomes 3, right? Becomes 3. And after that, we count down. We have 2, we have 1, right? And at 700 nanosecond, we changed the direction. So the number becomes to 2 again. Does this make sense? Okay. And also look at the clock. So basically the clock is flipping between 0 and 1, right? and every change happened at the rising edge of the clock. When the clock goes from 0 to 1, then the output will be updated. Does this make sense? Okay. And also the load signal at 100 nanosecond, we set load to be 1 so that we can load the external number into the counter, and the external number is always set as 3, right? So at this moment, we load 3 into the counter, and output becomes 3. And after that, the load was put low, so we disregard the external number, and now the counter is counting by itself. Okay. And finally, we have the direction, so we changed direction right here. Does this make sense? Okay. Let's say if at this is 1000 nanosecond. Let's say if at 800 nanosecond, no, if at 900 nanosecond I want to load another number, I want to load 5 into a counter, then what can we do? Obviously, for the clock at 800 nanosecond, we still have to pull the clock low, right? And then at 900 nanosecond, if I want to load a new number into the counter, if I want to load, let's say 5 into the counter, then I have to first set load to be 1, right? No, I have to first set the external number to be 5, okay? And I set load to be 1, which means I load something into the counter, and I set clock to be 1, right? Okay, and let's try if this works. And this warning means I didn't close the window here, so I close this window. Try simulation again. Okay, show full screen. So as we can see, at 900 nanosecond, external number 5 is loaded into the counter. Does this make sense? Okay. And if I change the D here, if I don't change anything, but change D, the external number D, to 5 at 500 nanosecond, right here, will anything change for the output? No, it doesn't change, right? Because we didn't set the load information to be 1, right? So we can confirm this. For example, I go back to 500 nanosecond, I can change the external number to 5, okay? And I can remove this line, close this, check syntax, and simulate again. And see, 5 is only loaded here because only at this moment the load is high, right? Okay, any question? No? Okay, great. So I believe project number 3 will be very simple for us, right?